say A and B. Let me denote the generators by A and B. And so this is an edge if this element G inverse H belongs to this set. Okay. So this is a tree. And why is it a tree? Because if you have a loop here, then that will correspond to a non-trivial relation among the elements of the group. But as it is free group, there are no relations. So this is a tree. And gamma obviously acts on it. So gamma acts on vertex set of T because say G acting on this vertex, say vertex associated with this element H is this. Obviously, if H prime is an H, that means H inverse H prime is in this set. And obviously that means this element GH inverse GH prime is also in this set. So that means the group also acts on the edge set. Very simple. The next edge.
So this is like the source and the range. Okay.
Which one?
This is you are going from G to H by A.
This is the Kelly graph of the group. This is the Kelly graph of the group? Yes, this is the Kelly graph. So
more like a groupoid, I thought.
here, of course, it is a tree, so it is also a groupoid, but it is really Kelly graph. So anyway, now you form the Hilbert space H plus equal to L2 of T0. T0 is my vertex set. Instead of PT, I will denote by T0. This is same as T0. And H set will be T1. So H minus is L2 of T1 direct sum C. I throw in an extra copy of C. I want to define the map phi from T0 minus the identity element of the group to T1, and that is done as follows. So phi of Q equal to unique edge on the path connecting identity and Q. So unique edge containing Q on the unique path connecting identity and Q. So let us stop for a moment and draw a picture because that may help you think. So this is really like, so you replace, draw a picture, A inverse, B inverse. Maybe here you draw, keep on drawing things like that. That's how this graph will look like. So on and so forth. So as it is a tree, given any two vertex, there is a unique path. So you start with the idea from the identity, go to that vertex, the last edge of that path, you call it phi q. Then you realize that this is a bijection. This is a bijection, and I have got my Hilbert space, and I forgot to silence this. One second. So now I have to define my representations. Of course, I know that L2 of T0 is so my Hilbert space. So L2 of T0 is really L2 of gamma. So the group is represented on that. Group acts on the edge set, therefore group is represented on this object. Therefore I define, so I have obvious homomorphisms from CR star gamma to L2 of T0, L2 of T1 on this part, the group is answer 0. Therefore it answers your question or concern last day. The group representation is not necessarily immutable. So I write down A of xi lambda equal to A xi 0 for xi from L2 of T1. Okay? So that is the representation. And now I need to define a map we call R from H plus to H minus. So H plus and the basis consisting of elements from the group. So these are EQ. Okay, this prescription is if Q is not equal to identity. So if Q is not equal to identity, this is this element. If Q is equal to identity, this is if Q is not equal to identity. And we know that this sister algebra has a trace, namely contraction by this vector if I define summation A G equal to A identity, then this extends as a trace.
One at Q.
This one?
No, the epsilon Q.
Yes,
One
sir.
at Q. Delta Q.
Yes. So that's how this is defined, tau, and then sort of it is the verification. First of all, I write down my A as 0 R inverse 0. So this is unitary equivalence. Therefore, I write my F like this. I have already got my H, which is H plus direction H minus. That already gives the grading. I have a representation, I have F, therefore that gives a one summable freedom module. Therefore you can try to calculate its associated trace, verify that that is really this one, therefore it extends to the whole of sister algebra. So this completes the argument for projections, not ideal moments. That is the only point missing. Yes.
If commutator.
Oh, so why is that? Why is that compact? That is the question.
Not compact. You wanted it to be one summable. So
One summable. Yes. So let us see that. Why is that so? That is a good question. So I say if commutator A is finite length for A coming from C gamma. Why is that so? That is for the following reason. So I take G, I hit it. So let us fix a G. Then I look at this class. All those Q such that G phi Q equal to phi of GQ. actually true except for a finite set. So this set, cardinality of this is finite. So this is true except for a finite set. And that is again a direct verification because all these objects are as explicit as it could be. So this is a direct verification, and that shows that if commutator G is finite rank, therefore it is first class. So this proves it for projections. For idempotence there is a trick. So the trick is the following: given any idempotent that is similar with a projection. Given any idempotent that is similar with a projection, therefore, from the fact that tau is a trace, tau of P equal to in that class will imply tau of E is in that class. So that will make that projection to be trivial. That will make that idempotent to be trivial. So this is general argument.
Is it not true for every Q? They are equal the way you find.
No. This is, I give you an example because otherwise, so it is not true for every Q. So why is that so? See, this set depends upon this group element G. So let us take a group element G, which is S1, S2, Sn, be a reduced expression of a